Welcome back. In the previous two videos, motion planning with waypoints and motion planning with A star, we generated a path. For example, let's look at the material with waypoints, motion planning with waypoints. If you haven't watched that video, please watch. This video will make more sense. So in that waypoint video, right, we did a curve fit. We find W1 for X hat and Y hat. We find W2. Now, within the context of control, basically these X hat and Y hat will represent a comment that we apply, that we use for path following purposes. And I'm gonna call them CX and CY. You can both use waypoints or A star, and then you will have a path that the system needs to follow closely. But regardless of the fact that you have a ground robot, airplane, a robotic manipulator, it is not possible to instantaneously follow these commands, CX and CY. And this is due to the fact that we have dynamics, right? You think about your car. You had hit the gas pedal, let's say to reach 60 miles per hour. It takes some seconds to reach that applied command. So your system has dynamics, and we need to consider the dynamics of the system for following the generated motion, generated path, in this case CX and CY. And I would like to, in this video, talk about how we can do that, and our friend will be feedback linearization. So let's jump to the material. Let's look at this non-holonomic mobile robot dynamics. And this can represent a fixed wing vehicle flying at a altitude, fixed altitude, car dynamics. This has a lot of usage, and hence there are different authors wrote many papers about non-holonomic mobile robots. In this case, if you look at this robot with wheels, so its motion toward the x-axis, its position, I'm going to call it px. Its motion on the y-axis, I'm going to call it py. And this motion will depend on the orientation theta of this vehicle. So let's say you have this orientation, then motion on px is dependent basically q, basically this is the tangential velocity multiplied by cosine of theta. How you go change in py direction is q multiplied by sine of theta, right? You have some velocity and you are basically multiplied by this sine. This is the how velocity changes on the py, or how py dot changes. Orientation depends on your W, right? Angular velocity. And basically your speed is dependent on the force you apply divided by the mass of the system. Likewise, W dot, angular acceleration, depends on the torque you apply divided by the inertia. So this is a fifth order system. It is a nonlinear system because of these Q cosine, Q sine terms. And again, F and T denote the force and torque control inputs. So in the literature, there are different techniques to control this system. And this is a hard to control system because of this non-holonomic constraint. And here, let me briefly explain what I mean by non-holonomic. Think about your car. You can easily go in this forward direction, but it is harder to go on this direction because, right, think about parallel parking. You need to do zigzag type of a behavior. And this is only because of your car is non-holonomic constraint. It is not omnidirectional. All right, so to control this nonlinear system, idea is feedback linearization, and this is where we are going to do that. I would love to refer to this paper written by Lawton, Young, and Beard in 2000, and this paper I'm going to cover in this video, that feedback linearization technique, one of the best techniques that I am also using in my research. I also would like to refer to this paper written by Deniz Kurtoğlu, myself, Yang Tran, David Caspier, and Eloy Garcia. We are also using a slightly extended version of the feedback linearization technique used in this paper. And the advantage of this technique is you can have less control magnitudes. I will explain in a second. So let's start with the content from this paper. Basically, instead of controlling px and py, we are moving that frame a little bit away from this px and py, and we are interested in controlling hand position hx and hy. So, and these two relations capture how hand position and in x and y are related with the actual position. There is some constant L multiplied by cosine and sine of this theta. So in this paper written in 2000, L is fixed. Now, in general, you would like to make L small as possible such that your hx and hy are close to px and py. But when you make it too small, your control signal can have large magnitudes. That's why in this paper by Deniz Kurtoğlu et al., we make L, instead of using a constant L, we used L of t. Initially, we make it large and then converge to a small value of L of t. L of L needs to be positive in all cases, such that you can avoid with this modification large control inputs. Anyway, so this is my 2 cents on this problem. So I'm now proceeding with the feedback linearization problem. I am taking the hand position of this vehicle and differentiating by 2 times. Then you can, after some mathematical arrangements, you can easily write this as hx dot dot and hy dot dot. This is the rotation matrix multiplied by force over m, TL over j, and these 2 terms. Okay, let's move forward. Now, for feedback linearizing this non-holonomic mobile robot, we are going to use this force and torque control inputs. Now, if you take this and plug it to here, right, first thing that you should realize, m will cancel out its effect. J over L will cancel with L over J. Then inside here, the remaining terms will be these terms after this cancellation. So now, these terms that you are going to see, we have minus sign, they are going to cancel the effects of these terms. And finally, this rotation matrix will be multiplied by this, multiplied by ux and uy that I'm going to talk in a second. And using the r theta, r minus theta equals the identity property, they will go away and you end up having this linearized equation that doesn't have any nonlinear terms. So if you cannot see this directly, just take this, plug it to here, you are going to see that you will directly arrive to this feedback linearized system. So we call this ux and uy to be the virtual control inputs, right? Our actual control inputs are f and t. So we just choose it like this to cancel out all the nonlinear terms, and we end up having this simple and nice virtual control inputs, in this case double integrator dynamics. Now, since you have a much simpler dynamics, you are right now in the linear domain. For example, you can select x1 to be xh or xhy, x2 to be hx dot or hy dot, and u to be ux or ui. You can write this in the state space form and then use, for example, for this control signal for both axes, basically, right, ux will be, you can think like this, if u represents ux to be hx dot, this is the first control signal with alpha and beta positive parameters, and c in this case becomes cx, and uy will be hy minus c y and h y dot. It will have this form. And remember, cx and cy are coming from the analytical solution of the least squares problem from the previous video. Now I would say for any positive alpha and beta, you can do command following, and your closed loop system will be stable. If you haven't watched the videos on my advanced control system series, it is another playlist. I am using one of the controllers that I cover in this video, and this video has a bunch of details. I am just doing state feedback here. In order not to be repetitive, I am not diving to any details. If you would like to understand all the details or more details about how we design controllers, watch this video, or take my word for it, this controller will work. Sometimes people also use minus c dot. You can also add c dot dot for, to accommodate the changes in the time varying command. There are versions of it, but let me use that version for the next problem that I would like to mention as the second example for the feedback linearization. Manipulator dynamics. So fully actuated manipulator dynamics often has this form. Okay, so here M is the mass matrix, Q is the configuration, and B is a nonlinear function that stores corollaries, centrifugal, gravitational, and friction terms, and T is the torque control input. I also would like to include this as another example. To feedback linearize this system, consider this torque control input. Our virtual control input also pops up here. So once you insert this torque to this system, basically you have this equals to the applied control input. As you see, these terms will drop out, and mass matrix is invertible. And then you arrive Q dot dot equals to U, again, linear form, all the nonlinearities that comes from M and B dropped. So you can control this simplified system using virtual control input. And you can use, for example, this type of a controller that includes C dot, C dot dot. This is your command that comes from least squares problem or generated trajectory. You can also implement this without these terms as well, which you will recover the control signal I just covered here. I just wanted to write for different examples, different types of control signals. You can use both of them. Now, in the first example, we did feedback linearization by defining another coordinate system, right? This hand position. In this manipulator case, we directly did feedback linearization. So there are techniques. These are the two common techniques. And also, of course, there are systems that you cannot feedback, you cannot linearize through feedback. In this case, you find a linear model of your system on desired the desired equilibrium points, and then design controller for each linearized system. And this will allow you to control the nonlinear system around the operating points of interest. This is called gain scheduled control. And I made again, you will find another video on the advanced control systems lectures on that playlist. I am not going to dive into the details of gain scheduled control here because it requires more understanding from the control theory. But feel free to watch Advanced Control Systems lecture series. Another final question you may have: what happens if there are uncertainties in M, B, and M, for example, right? If the actual B and M differs from the M and B that I am using to feedback linearize this system, then there's a problem. So to handle uncertainties, I also have playlist lectures on adaptive control and learning. You can watch those videos to understand how we can suppress the effect of uncertainties. All right, take care.